recurrence relation, we need to solve it. And in this problem, the biggest difficulty is this flow function. So we need to find a way to get around first. Later, then we overcome that difficulty. Okay? So let's start our solution. All right. So let's first determine the basic operation. When we do analysis, we want to count the number of basic operations. Here, there is a division, right? Division by 2. Usually, the division is very expensive. The regular division is very expensive comparing with addition. But here, the division is so special, divided by 2. Division by power of 2, that's very easy. In computer science, we just shift, right? You shift the position. Then you do the division by 2 and a power of 2. So here, this is a left shift operation. That's very cheap, very cheap.
Isn't it a right shift? Right shift makes it smaller.
Right? Yeah, division by 2 smaller, right?
Yeah, that's a right shift.
Right shift larger, right? Right? Oh, right shift. Oh, okay.
If you're writing the binary number
Yeah, all right.
with the most significant bit on the left and the least significant on the right.
Right.
So you shift right to drop the lowest.
Okay. Shift to the right. Smaller. Oh, yeah. Shift, oh, yeah. Shift to right, smaller.
Yeah.
Okay. Yeah. So right shift. Yeah, you're right. Okay. Right shift. Yeah, because sometimes when we talk about shift on what, right? So here, if you shift the decimal point, that becomes smaller. So shift on what? Yeah. All right. So let's get that right. Okay. When we talk about shift, what do we shift? Yeah. So, right. So, yeah. Here, I got confused. So I need to, find what is really, what do we mean? Okay. Shift what? Okay. All right. Yeah. Anyway, so it's a cheap, very cheap operation. Yeah. Comparing with this operation is faster than addition, much faster than addition. Addition, you need to do a lot of operation. Okay? It's faster. So that's why we use addition as our basic operation. Slower, right? Slower. So let's use the slower one, right, as our basic operation. Okay? Now, we need to count the number of additions when we solve this recurrence relation. Okay, all right. We define a new function, a of n, as the number of additions. Okay, number of additions. Now, we get a recurrence relation of this a function. Recurrence relation about a function. In order to solve the whole problem, we need this many addition, all right? But we split. Remember, we, get size by half. To solve this problem, we need a of this number operation, okay? But there is one extra bit. Plus, remember, yeah, one more bit, right? So one more, yeah. So plus 1, all right. So the recurrence is for like this. A of 1 equals 0. Yeah, because 1, you do 0 addition, right? When A equals 1, you do not do any addition. So the base case 0. Now let's find the solution for this recurrence relation. Okay. Similar to the original one, but the base case slightly different. Yeah. All right. So now still we cannot get around that flow function. So we still need to find a way to deal with it. All right. Examine the property. even, odd, right? So we know for even number divided by 2, that's an integer, no fraction part, so we just take it. For the odd case, we need to drop some fraction. Okay? Yeah. So that's the definition of the floor function here. Okay? So based on that, okay, so our strategy. Okay? Yeah. So this strategy we used many, many times. So here, so let's still use this strategy. Start with a simpler case. Yeah? So this even case simpler. So first let's assume this n is even. Okay? And later let's worry about the harder case. Okay? All right. So making assumptions. Let's find the best situation for us. Okay? So we want to find a solution for the best situation. Okay? How to choose a simpler case? What do you wish to have? We wish to have even number, right? An even number. Okay? So what do we wish for? In order to make this equation simpler, we wish an even. Okay? Let's go another step. From this equation, in order to make this equation simpler, we wish n over 2 even. Okay? And so on. Yeah. We'll keep going and until, so at the end, we want to have all the relatively simple case, we want n power of 2. That's the simplest. So if we, under this assumption, then we can ignore all the floor function, right? So no difference. Yeah. So all integers. So that's the best we can have. Yeah. So let's assume that, right? Yeah. Let's assume the power of 2 size. Okay? Power of 2 size. Let's solve it under this assumption. So we can rewrite our recurrence relation, this time using power of 2. When you do division by 2, another power of 2, right? So you can see no fraction involved. So that's the perfect situation we have. Okay? All right. So you can see this is our new recurrence relation. All right. So now we are ready to find a solution. So let's do the work here. Yeah. So this area, so let's do the computation work. Okay. We will list all those equations, the first one, the next one, right? So keep, every time we reduce the size by half, okay, we keep going one after another until we reach the bottom. Okay? That's the bottom equation. Yeah. Now, because you can see if we add up all these equations, we can have a lot of cancellations. Okay? So let's do the summation on all the equations. Cancellation like this. Left, right, the same term, cancel out. Okay? Another, okay? You can see this kind of diagonal cancellation, right? This kind of diagonal cancellation, okay? Until we cancel out all these terms. Okay? Remaining terms, left-hand side, A of left. But now the question, right-hand side. What do we have at the right-hand side? Right. Because A term, this is 0. Base case 0. Sum of all the ones, how many equations do we have? Can you count that? How many equations do we have? That's the same number of ones. Can you find that? Remember the counting by reference. Eh? So I gave you this simple method before, counting by reference. Okay? The first equation corresponds, let's use the exponent as the reference. Okay? K minus 1 the last one, 1. From 1 through k, right? From 1 through k, how many lines do we have? Okay? You count from 1 to k, right? K, right? 1 corresponds 1. Okay? One line, one number. Okay? So you have k. So that a function equals k. Okay? Equals k. Yeah. So yeah. Counting by reference. Okay? Yeah. All right. Now let's go back. After that work, let's back to the conclusion part. We need to make conclusion. Okay? All right. Result. Yeah. So what's the result? Because the result should be in terms of n, not in terms of k. Right? So that's why we need to find n expression for k. Yeah. K. We should not use k. Okay? We should not use k. We should use n. All right. So let's go back to n expression. A of n equals log base 2 of n. Yeah. So this is the result. Okay? Yeah. Under the assumption n is power of 2, we find a solution. Okay? But this is under that assumption power of 2. Okay? We need to go to the general case. Okay? We cannot stop at this point. So we need to keep going, find the general expression for arbitrary positive integer n. Okay. Let's make a guess. Okay? Yeah. Before we go further, let's make some guess. Yeah. In math, we need to make a lot of guess. Okay? Guessing is very important. Especially at the critical steps, you need to make some guess. Okay? So here, let's make some reasonable guess. Okay? We know the meaning of the a function, that's the number of additions. It should be an integer, right? Addition. Number of addition, 1, 2, 3, 4. It must be an integer. But this expression, not necessarily integer, right? For arbitrary n, integer. How can we get integer from this expression? This is not. Let's make some very small modification to make it an integer. Is there any simple way to do it? As simple as possible. And also make it close to this number. We don't want to, make big change. We want to make very small change. Some special function. Do you have any special function make a non-integer to integer? Any special function? Make a non-integer number to an integer number? Floor, ceiling, right? Floor. Right? Here, let's use floor function. Right? Our guess, floor function. Integer. But you make this guess, you need to prove it, right? It could be wrong, right? How do you convince people this guess is correct? But the good thing is if your guess is correct, then you have many ways to prove it. So here, guess, then prove it. It is much easier than discover it. You do not know anything. You just try to discover it. That is very hard. But if you have a good guess, then you use many tools, many methods, we can prove it. Yeah, here, we take that approach. Next, we want to prove it. Mathematically, we want to prove it. Mathematical analysis for the general case. We have a guess, so let's prove it. Guess and verification approach. Yeah, so you need to make the right guess first. Yeah, we hope it's right. Okay. We guess that a of n is this function, floor function. Okay? Yeah. So there is some reasonable, we did some good work here. Yeah, it's another random guess, right? It's not a random guess. It is a close, good guess. Okay? Now we just want to prove it, the proof. Okay. How to prove it? We use a powerful mathematical tool to prove it. Very powerful tool. Okay? You learn in discrete math, you learn it. Mathematical induction. Mathematical induction. Yes. Here, let's apply mathematical induction. Okay? Mathematical induction. Yeah. First, we check the base case. Yeah. 3 steps, right? Mathematical induction, there are 3 steps. Let's follow that 3 standard steps. First, the easiest, base case verification. When n equals 1, obviously it's correct, right? So that's obvious. Okay? So first step, complete it. All right, yeah, based on the given condition. Step 2, all right, induction assumption. We make assumption. That's the induction assumption. Okay? Yeah. We assume it is correct under some condition. We assume it is correct for all the k between 1 and n. N, some positive integer, okay? N, just some positive integer. Some, okay? Yeah. It's there somewhere, it's there, yeah. And the k, if between 1 and n, we have this, we can assume all these functions have this expression. Induction assumption. No. Yeah. So that's our step 2. Okay. The hardest step, step 3, we need to show when k equals n plus 1, we still have that. Our goal, yeah, we still have this expression. Then, based on the mathematical induction, it is correct for all arbitrary positive integer n, all correct. Mathematical induction. So that's why it's so powerful. Okay? Why it is so powerful? Okay? Yeah. So we can show it's correct for arbitrary n. Well, now let's do the step number 3. Yeah. So that's the real, the biggest step, the hardest one. Yeah. All right. So let's work on it. Let's consider 2 cases. Proof. Okay. Proof. Okay. The first case, n is an odd number. Yeah. This is we only consider 2 cases, odd and even. Yeah. But we feel odd number is slightly easier, so let's work on the easier case first. Slightly easier. Okay? Because odd number plus 1, it's an even number. Okay? So that's why we like that. Okay? Let n equals 2s minus 1. Okay? Odd number, we can write this general expression, right? 2 times integer s minus 1 with s greater or equal to 1. Yeah? So we have that general expression for an odd number. Now let's evaluate a of n plus 1. Plus 1. So a of 2s. A of 2s, based on the recurrence relation, right? Yeah. Can we use the recurrence relation? We can, right? Because A follows that recurrence relation. So by the recurrence relation equals A of s plus 1. Division by 2, so 2 is gone. Okay? No remainder, no fraction, skip it. So that's why we choose odd first. Okay? Because this step is very easy. Okay? All right. Now, let's go to the next step. When after we have this expression, let's consider the range of S. What is the range of S? S equals n plus 1 divided by 2. N plus 1 over 2. Is this number less than or equal to n? When n greater or equal to 1? Definitely, right? You multiply 2 here, cancel out n greater or equal to 1. It's correct. Okay? So this expression is less than or equal to k. Based on our induction assumption, do we have this? Yeah. That's why induction assumption is useful here. Okay? Based on our induction assumption, this S falls into this category, okay? This range, right? This range. So we can apply this formula on S. Yeah, that's obvious. Okay, all right. So when we go there, we have this expression. How about that? Induction assumption. Yeah, that's why we can go one step forward. Okay? All right. Now the right-hand side. So here we get an expression for the left-hand side. Now let's do calculation on the right-hand side, and we hope we get the same expression. Then they are the same. Okay? So now let's work on the right-hand side. Hey, n plus 1. Okay? 2s, right? Yeah. 2s. Okay? Plus 1. 1 is gone. 2s. Okay? Log base 2. Log product of two numbers. You know that, right? Yes, it's plus. Okay? Plus 1. Is that plus 1? Okay? Yeah. So we simplify, we get this. Okay? All right. This is an integer, right? Floor function, this integer inside, can we move outside? Floor function, because this is integer, right? Can we move outside? Okay? Let me refer to a formula. Yeah. If we move outside, we get this. But if you are not sure, let me give you the reference of the formula. Appendix A. On this page, there is this formula. Okay? The formula I put here. That is any real number plus an integer floor function, we can move that integer out of the floor function. Okay? Yeah, that's simple. So here we use that function. After that formula, after we use this formula, you can see they have the same expression. This, they have the same expression, right? When they have the same expression, it is correct. Right? This formula is correct. That is the step 3 of mathematical induction. So we prove the whole statement. Yeah. It's correct. Okay? So our guess is correct. Yeah. So we have that. We complete. Yeah. No problem. So after this, nobody can argue with you. Okay? Yeah, it's correct. Yeah. Mathematical induction. Yeah. Yeah. Any question? Yeah. Hope you can understand. Yeah. Mathematical induction for your discrete math. I know it is a hard topic. For discrete, it's a hard topic. Yeah. But here we have to use it. At this particular situation, you can see the best tool we need, mathematical induction. The best tool. Other than mathematical induction, how can we solve it? Right? Yeah. Good. Yeah. Oh, that's the case 1. We have case 2, right? Even, yeah. Actually, the case 2. Oh, so that's why we only solved 1/2. We have case 2. Yeah. Actually, case 2 is a little harder than this one. A little harder than this one. Yeah. But still, really, oh, yeah. So someone may know this. Yeah, you should tell me. Yeah, I forgot. Well, continue. But I have that part. Yeah, I have that step. Okay. When n is even, this time n equals 2s. This time we need to calculate 2s plus 1. Okay. Recurrence relation, we have that. After that, this one drop it. You can see that one drop it. Okay? So we check the range of s, 1/2 of n, definitely between 1 and n. Right? So we can still apply this formula. Okay. Yeah. This step, almost no difference comparing with the previous one. Just copy. Okay? Make very small adjustment. So this step, trivial, but next step, much harder. Next step, from this side. Okay? For this side, this time 2s plus 1, odd number. You can see this time log base 2, but plus 1. We cannot get 2 out, right? We cannot get the product of 2, product of 2 numbers. We can't get that situation. This time, we feel, the previous technique we cannot use. Right? Now, we need another important formula.
Could you just convert it a 1 into log 2, because plus is multiplication of logs? So.
No. Log base 2 of 2. But this plus, how can you get around it? Right? We cannot drop it, right? You cannot drop it. Don't drop it. Don't tell me we focus on the dominant term and drop. No. Under this situation, you cannot drop. Okay? When you can drop, you try to get a growth function, right? You try to see the approximation order, then you can drop. But don't drop here. Okay? Here, we cannot drop anything. All right. But we need another formula. At this point, some important formula is very important. So we need another formula, still on this page, but there is a different formula. Okay? On this page, appendix, there is a formula like this. Okay? All right? Ceiling function. It's not floor function. Okay? Log base 2. n plus 1 equals the floor function and plus 1 outside. Okay? That's the formula on this page. Okay? We can prove it. Okay? If you want, you can prove, but it's not that easy. This proof is not that easy. No. Here, let's just do it. Okay? Later, if we have chance, we prove it. Okay? Yeah. First, it's correct. Yeah. Let's apply this formula. Why this formula is good? Because log base 2, there is a plus 1 situation, right? n plus 1. If this number plus 1, then we get that 2, right? That's nice. We get that 2 out. Okay? Yeah. So that's why let's work this number. Floor function, right? Floor function, we can move 1 to the left-hand side, minus 1, right? So the floor function, then this expression, it's the ceiling function, plus 2, minus 1. Okay? All right. This 2, we can factor this 2 out. We have 1 plus this s plus, but that plus 1 and this minus 1 cancel out, right? So we have this left. Okay? So this expression, we get this, but remember this is a ceiling function, not floor function. Okay? That is the ceiling function. But the ceiling function, can we apply this formula another time? Yeah, your ceiling function n plus 1, our ceiling function s plus 1. Do we have floor function s plus 1? Okay? Yeah, so we prove it, the same. See? Same. Okay? So here you can see our case, even case, we need to apply this formula twice. Twice.
Can you repeat that one more time?
Repeat which one more time? Yeah, you also asked me. Yeah, what's your question? Let me explain.
So
Wait.
I guess I'm confused at the line where you're.
This line?
Yeah.
All right. What's your concern? Yeah.
I was just
Sure.
going through converting from flooring to ceilings.
All right, good. I mean, 2-step converting. All right. Okay. In that case, let me work. Yeah, because I skipped some steps, right? Let me make all the steps